Can you hear me? Hello? Hello?
Yes, sir. Yes, sir.
Can you hear me?
Yes, sir.
Okay. Boa noite. Can you hear me? Hello?
Yes, sir.
Okay, that screen is visible or not?
Sir, it is visible.
Okay, fine. Thank you. We'll start with product space. Before that, let me tell you the subspace topology I have written wrote that I will post today. I want to just reread again. I want to read again to check subspace topologies. So that node I will post today. Now product space. Here you have two types of product. Product spaces, space of topological spaces. Actually, your finite product, infinite arbitrary product. Basically, infinite product. This finite and infinite means topological spaces. That means you have two things. Finitely many and here infinitely many. That infinite may be uncountable. Infinitely many. This is the meaning. The finite products means products of finitely many topological spaces. The arbitrary product means basically any family, finite or infinite. So particularly infinitely many. That means even uncountably many. But this is at your stage right now, it will be a bit difficult to understand. So that I'm starting with only finitely many. Okay, so that suppose so finitely many, that means you are taking this x1, tau1, x2, tau2, xn, tau1 topological space. Actually, what we are doing for n topological spaces is that actually same as to do for two topological spaces. Okay, so some people, some books they start with only two product of two spaces, but the idea is same. Suppose these are topological spaces. Then you have a set X product of this. This is called the Cartesian product. This is basically all n tuples. All n tuples. This is the product of X. Now on this, I want to give a topology. On this, I want to give a topology which will be naturally related to give a topology. Tau on X, which is naturally related to each tower. Actually, I told you our model is like R. You have taken R to the power n, which means actually R cross R n times. Here the usual topology is naturally related to the usual topology on that. Okay. So that how to give this topology, natural topology. Okay. Naturally, it will be more clear when you further study the product topology. Okay. How to give this? How to give tau on X? Well, in fact, we do not try to define the entire topology. We try to define that each point or through base. That's why it's important you understand the concept of base. Here, when a collection of subsets of X will form a base, that condition you have. So here you take the condition this, take all this, B equal to, I'm writing this way, Ui I 1 to n Ui belongs to tau I 1 I less than equal to. That means we are taking this. Taking all the open sets from the tau I, taking the product, okay, and this will be a base. You can check. It won't be a topology. It won't be a topology. Won't be a topology. So that you do this. You can easily verify that B is a base for a topology tau on X. So what is the property of the base? That I already have given that. I think Sarthak's node I put there. Sarthak's node that is there. That when it will be base, when it will be base. So we check that. Basically, union of all this has to be, look, if you take x1, x2, xn, itself is a member of this. This belongs to B. So the first condition is satisfied. Okay, you'll have to show the second condition. Second condition is what? Suppose you have two members, their intersection contain another member like that. That you'll have to check. Okay, so check the second condition. So this will be a base for a topology. This topology is called the product topology. It will be unique topology. It means also you should know this is the smallest topology containing B. That is called the topology inherited by B. So that this topology tau is called the unique topology. That's why you can use the word the word used, article used, it is unique. It's called the product topology. On X, where X is the product. This. Okay. Look here, you said that will be enough that you know the base. Okay. That means base is this. Okay, and recall. Y, I, 1 to N, Y belongs to tau Y, 1 I. This is a base. This will be good enough for us to know. Now the next thing is that which is important, that if you have this, like I told you last time, like R square to R, you have the projections. That means if you take X, Y, this is called the first projections. Okay, X. And second projection is this. So that is usually called geometry, the projections. Project. Similar concept we can have it here. Okay, look, I call it pi I, ith projection from this. Okay, if you this I is a one of the I, this I is a variable I, but if you want, you can take this jth projection. I 1 to N to xj. That means you have a point tuple x, x1 to xj, xn, that we are taking xj. Okay, right? This is called the jth projection. Projection of x product. Obviously, it is onto xj. If you take xj and then put up anything there, that will be pre-image, jth projection. Some people write because pi actually stands for p in Greek alphabet. Some people use this notation p instead of pi. Okay. So that in some book you may find pj. This is called jth projection. So that in fact this base and these projections, they give you everything, every tool to handle. They give all the tools to handle product topology. You need this and this projections. Okay, now look, the first projections, now you have got a topology which is a base, and here already you had the topology. So this is a map between two topological spaces. The question you can ask first thing whether pi j will be continuous. Okay, so that result one. Right, late, so x out tau y here, family of topological spaces. Then pi j writing the product topology to this is continuous and this is a good thing and open for each chief. This you have to know, continuous and open. Well, you'll have to show the inverse image of an open set is open. Now look, you take an open set, uj belongs to tau j. Look, here pi j inverse uj will be what? This will be all the points whose only restriction is that jth coordinate should be here in uj, jth coordinate. For other coordinates can be anywhere. So this will be actually x1 cross x2 uj you can check that. If you do the projections, you will exactly get uj. Because only coordinate, this means that your jth coordinate has to be uj. For other coordinates, you do not have any restriction. That means other coordinates you can choose anything. That exactly I did. But this is open because this is actually basic open set. That is the proof online. Only thing you'll have to understand that pi j inverse, in fact, I will teach you at the end, infinite product, if I have time. There you need this basic thing, this idea. The pi j inverse will be this. Okay, right? So this is continuous. For open, all I need to check the image of a basic open set is open. Because other open sets are as in the union. So look, so that I need to check the projections pi j basic open sets. Look, for open map, you can always check. That is also for continuity. Inverse image of a basic open set is open, and image of, and for open image of a basic open set is open. Basic open set. Okay. So that look, this pi j, this is a basic open set. This will precisely give you uj. That is open in this. This is the proof. So pi j is open. I have just proved the image of a basic open set is open. That is good enough to show that the pi j is open. Pi j sends every open set in the product topology to open sets in the factor space. These are called the factor space. Okay, so that pi j is open and continuous. That's all you need to know. Pi j is open and continuous, but pi j here need not be closed. You should. Pi j will be open and continuous, need not be closed. Right now need not be closed means need not be a closed map. Okay, I'm just giving an exercise. Right now check that. So you'll have to find a counter example. That it need not be closed. Okay. So that now I'm not saying that, but you should have the emphasis that projection, each projection is open and continuous, but need not be a closed map. Okay. I can give you the, but that will have to prove. This is an exercise there. Okay. Hmm? This is easy to do that. Take pi 1 first projections to this. That means xy going to x. I think I'm going to do it. No, look. If you take a closed set, okay, right? Now look here. Hmm? Let me see that. This thing I want to take this set. Call it whatever it is. Split this. Okay. Got it. This is closed in easiest way to check that its complement is open. Whatever point you take and that you can always take a ball, maybe small, that will be entirely contained in the complement. So this is closed. In fact, intuitively, if you have two dimension, then if you have something one dimension similar to, that will be closed. Similarly for higher dimension. So this is closed. And what will be this pi 1 a? Look here, projections. First projections means what? You are taking this thing, this point, this point, this point. But this is coming what? 0 will never get. But this is not closed. In R. So that this is an example. This is Willard gave an exercise, page 57. 80 projections maps. Okay, but he's saying, so this is, here is an example. This is not closed. Okay, right. He has actually asked to prove that what I did, that he is talking bit of projections and that projection is continuous and open and projection need not be closed. But now look, he's saying if you take this map, I is the unit interval. It is got the usual topology. This projection var. The second projection is saying sure that is closed. Here, I'm not going to do the problem, but I'm telling you, in order to show it is closed, actually you'll have to use the fact I is compact in R. Okay. Look, these are metric spaces. This is on the, so that you can ask about the product metric, whether that will give you the product topology. Well, that's the question I'm going to. So these are the product metric you can take. That is, this is a subset of this R square. To the usual product, usual metric, that topology. That will give you the product topology. Then let me put you that question there. So this will be closed, but you need to prove use this, and you can use sequential characterization of closed and compactness here. Sequential characterization. I'll come to that problem later on again. Sequential characterizations of compactness and closed sets in a metric space. Okay, since I have landed here with the metric space, let me discuss this problem. Suppose we have two metric spaces. Now on X cross Y, you can define the product metric in three different ways. D cross O. Okay, three different ways. Okay, one is the usual what to do in R square. Okay, R square you do what? Look, you are doing this. If you have the metric, look, you have this. When you do this, usual distance in R square, this actually you give x1 x2 square plus y1 minus y2 square with this half. But this is d in R. This is also d in R. Okay, that is your taking. So that this way you can take that, the one place you can do that. That is usually called the product metric. That you, I will take this x1, y1, x2, y2. So this way you will do that. This is this t x1 x2 square plus rho y1 y2 square and this. This will is a metric that you can check. This is a metric. The way you check this is a metric in R square. So this will be a metric. But since this square root and that, people often don't like that because when you do some calculations, it becomes messy. So that there are two other metrics. So D cross rho, this is called the product metric. Well, now the product metric, now you can see why it is called the product metric. Because this will give you tau D, the topology. And this will give you tau rho. Now the product topology, this is a question. Tau on x cross y is generated by T cross rho. The T cross rho is this metric. This should prove. Okay, the product topology tau on x cross y is generated by this. Okay, so that what the problem I gave you that I cross R can use. So basically, instead of product topology, you can go by the product metric, which is exactly you do it in there. When you deal with R square Rn, that exactly we do that second projection. Okay, this is closed. It's a closed map. The product topology on this generated by this, so we are allowed to consider them as usual metric space. So basically, it's a metric subset subspace of R square. Okay, so and you can use already the facts you have known the last semester. So this is a closed map, but I compact is required. That you need, that you will be using. Now the thing is that I already told you that this is not a good description because square and square root are coming. But then what you can do that you can define two other metric on that. Suppose you have this, that of course you can extend to the finitely many metric spaces. Now you have another metric, call it sigma 1. X1, Y1, X2, Y2. I think this is called the box metric. Look here what I am taking. Okay, the distance of this and this. Okay, so this means what actually you are doing. Suppose this is your x1, y1, this is x2, y2. Okay. Look what you are doing. This is your x2, x1, this one, and this is your this one. So distance you are going this. Okay. Previously distance you are taking the usual distance, that is actually this diagonal. But here you are taking this. This will give you a metric. But in fact, this is easier to handle. Okay, this is easier to handle. And another metric you can take max of that. Like sigma 2. So how do I know these are will give the equivalent metrics? They are all equivalent metrics. That means they will give the same topology, product topology. This will be also metric. And you can check the D cross rho, sigma 1, sigma 2. They are all equivalent metrics. This you can extend to the any finitely many metrics, equivalent metrics. On X cross Y, so that they give you the same product topology. Product topology on X cross Y. Often for calculation, this is the, I think we usually choose this one. This is basically, even this is also easy to handle than the square root wala, but it is also, it is easier. Sigma 1 is easier than sigma 2 to use, to compute. Okay. In fact, in next semester we'll be doing function analysis. Function analysis you actually use this one. Okay, so that what I discussed, the product metric and product topology. Product metric and product topology. Okay, right? And product topology, you should know that we have basically done it through basic open source. And you have the projections. Projections, they're open, continuous, but need not be closed, because already I have given one example where it can be closed. But in general, it not be closed. Special cases it may be closed. Okay, so this much you need to know about the product topology. Okay, but now to have this, so I can give you some exercise, so result, you can prove that. Okay, that I'm giving, what I'm giving. Okay, let me give you this. Result. Let xi tau y be a family of topological spaces. Then 1a. If each xi tau I is first countable, so is, I'm writing this, the product topology. You can give a name product topology where specifically I'm writing with respect to product topology. Well, you have each projection open and continuous, whether the converse is true. Is the converse true? That means if this is first countable, whether each of them will be first countable. Okay, that's the question. That you should, if each xi tau I is second countable. When you have the product space, if we do not mention anything, we take product topology. Is second countable, so is here again you can ask this question. Remember, if you want to prove it, you'd all have to go through only projections. That's the map app. But projection is good. That is not only continuous is open. Does it help to prove that if this is first countable, then this is also first countable? Similarly, if you can same proof, basically same technique of the proof will work here. If you can do that, see what I'll do. If each xi tau I is separable, so is again the same question you can ask, is the converse true? Okay. Make sure all these questions you should do it. Or you can ask Saurabh, because I will look at my note while setting up the paper. What I have not done and left as exercises. Is the converse true? Either you should do it yourself, do them yourself, or you should ask Saurabh for help. Okay. So this is the thing. Actually, these are converse also true. That you should. Okay. How do you prove that? Suppose this is first countable. Suppose you are assuming this is first countable. Okay. Now phi I to xi. Okay. Right. Well, take a point xi. You are assuming this is first countable. Now look, take a point, any point here, xi. Okay. Right. Now look, you can fix other things. You can take anything like that. But this you can keep fixed. Only this will be changing if you vary here. So this you can take. So choose. Belongs to the product. Well, so that this is first countable. So this has a, but call it X. So there exists a countable local base. Countable local base Px at X in the product space. Okay. Now we take U belongs to Bx. Local base. Okay. Now look, U first of all is open and X belongs to U. Okay. But by the definition of the product topology, that's why I'm doing it, how to use that. Product topology, by the definition of product topology, because you know how we got the base in the product topology. All these products. So there exists Uj belongs to tau j. I'm using different notation because here I have taken fixed notation such that X belongs to 1 when. Okay. Now if you take phi I X, it belongs to phi I let me see that. Look, pi I X is precisely your X pi I X is exactly Xi. This is open. U. This is also open. But what I needed to do that, there exists a countable local base. That means U belongs to Bx. Sorry. This is fine. Okay. But where do you start? This is also open. But my starting should be different, right? What should be my starting? This is where, but I should start with this UI. And I need to find a base so that what I do, well, this is fine. This you got. I am not complete. I have not completed the proof. What I am saying now, okay, this much you get. Okay, this is open. This is open, but you should check. Look, U belongs to Bx. So this is pi I. Sorry, this is pi I. This is open there in xi tau y. So that what you should check this pi Bx. That means these things you are keeping fixed. Only xi you are changing. Pi Bx, that means pi Bx look, I have prepared this note. I have told you that when you have the function image, its coordinate will be less. So that here the pi is a function. Okay, so this is countable. So if you are taking the image of that, so this is countable. All you have to check here like this. This is a base, local base at xi in xi. That you'll have to check. I have used open. Have I used continuity? I have not used yet. That you should think how to use that. Okay, you need continuity also. Because will be starting with any open set here. So inverse image will be open here, and that will contain a point like that. That you'll have to choose where this will be this. So you will need continuity. I have not used continuity. I have not completed the proof. You need to complete the proof. Okay. So that those things will happen. Okay. Fine. So this much is the product topology. Fine. And let me tell you something that. So the product topology, when you have this, suppose you have this and you have this. I'm calling this tau product topology. Okay. And you have map projections. Usually use the same notation, but here it is variable notation, here is a fixed notation. Okay. If you don't like it, you can take pi j here. Then you will have to j here. Okay. So that, because I want to define the quotient topology now, but the idea is that and that is another nice property of pi I. So suppose, let me explain that. Forget about this for a while. Suppose you have y tau and you have x here, but you do not have any topology and you have a map here. You have a map here. Okay. Now, look, I want to give the topology. I want to give a topology here. Call it sigma here. I want to give a topology here such that this is continuous. You will say that is very simple, because if I take tau discrete topology, every subset of x is open, then this will be continuous. If tau is discrete, then any f, then f x tau, doesn't matter what is your sigma, this is continuous. But that is the largest topology. So then that means what should be a natural question? Does there exist a smallest topology such that this is continuous? Does there exist is A, should be da actually if I have it. Smallest topology tau on x such that is continuous. Well, how to answer that question? Look, if it is continuous, then first of all, I need this. All this should be open in tau. That means I should have this. Otherwise, it won't be continuous. This should be a subset of tau. But still, one condition you have got, that is necessary condition, smallest topology, small topology, that it has to be contained in this. That is one condition you got. But the thing is that still you have not got the full answer, because still you do not know about tau. Tau still can be discrete, the largest topology. Question is that this one, does it form a topology? Only this collection on the left. Okay, that's the question. So let me write again. Before that, let me tell you something, remind you. Some people you are using, suppose you have a map, just map. Okay, and A, B subset of X, C, D subset of Y. Then these things are true. That A, FA union B is FA union FP, B F inverse C union D, F inverse C union F inverse D, C F inverse C intersection D. These things you will always need in topology. They behave nicely. But one thing I am not given, that means this thing. They need not be equal unless f is 1 to 1. Okay. So why it is like that? Okay, all you can prove that if you have this, then obviously it is here, it is here. Okay. But if it is not 1 to 1, you can check that. This is your x. This is y. Suppose this is A. Okay. And this is B. Now look, when you go for FA intersection FP, look, two things can have the same image. Here I am taking the different. समझ गया? So that will be in FA. If it is not 1 to 1, it will be FB as well. So it will be there, but this one will be in the intersection. So that it will be superset. So be careful. This is for not, this is true. Okay. For the inverse, you do not have problem. It is both preserved under union and intersection. But when you go in the straight direction under F, intersection is not that preserved. That's the example here. But if it is 1 to 1, it will be there. Why I'm saying this? Now look, here we have a map. Okay. So take tau equal to, look what tau I'm taking. Tau you are taking this, what you are taking? F inverse B, B belongs to C. Okay. Is tau a topology on? If it is a topology, then obviously it will be with this x tau, it will be continuous because exactly I am taking this. Is tau a topology on x? Okay. Well, look, F inverse y is x. F inverse phi is phi. And two things, F inverse B1 intersection B2 is F inverse B1 intersection F inverse B2. Look, B1, if B1, B2 belongs here, then they belong here. Okay, but B1, B2 belongs here, then B1 intersection also B2 belongs here. So this belongs to tau. So that means this belongs to tau. And F inverse union Bi, whatever I you take. Okay. I need to show this is belongs to tau, but this belongs to tau. If each Bi belongs to sigma, this also belongs to sigma. So by this definition, this belongs to tau. That means this belongs to tau. So this will be a topology. It's a topology. And obviously this is the smallest topology, which makes F continuous. This is a topology on X, smallest topology on X, which makes F continuous. But now suppose I do not have one map, I have many maps. Then what will happen? Then it will not be a topology, but what will happen? Suppose that means what I am saying. What will happen? The question. suppose you have some index set is there, and for each I belongs to I, you have a map. Okay, suppose. Then does there exist a smallest topology? Does there exist smallest topology? That should be on X such that each smallest topology tau on X such that each okay H. Well, now you say, look, necessary condition, I need all these things. Fi inverse phi, phi belongs to sigma, I belongs to I. They all should be in tau. They all should be in tau. Okay. But the question is, it need not be a topology. Will it be a base? Will it be a base for a topology? Tau on X. Will it be a base? Or you can construct a base out of this. What does it mean? I have not explained that. Okay, right? Will it be a base? Okay, that's the thing. Well, if you want to have the simple case, I will take I 1 to n. Take I equal to, first do it the simple thing. Okay, so that take I finite. Infinite case I will handle later. Infinite case it will be something different. Okay, right. Got it. So will it be a base for a topology? That's the question. That you should check. This is exercise. Why I did? Because if you take each y sigma, okay. Okay. This is the thing. Okay. I can modify a little bit this question this way. Look what I can modify. I take xi tau I. This is what I am doing. 1 I less than equal to n, and x you take this. Okay. The product topology. The question. Tau. First answer this specific question. So that you have these projections. And each projections is open and continuous. That we have proved. Open and continuous. My question is that is tau the smallest topology on X such that each pi I is continuous. Look, if you want to proof is method should be very simple. Suppose you have another topology, another topology such that X, don't confuse with that sigma, previous sigma. Suppose it is continuous for each I, this is 1 to n. Suppose, then you'll have to show that if it is possible. That will be the answer, because already you know the product topology is continuous. I'm saying more smallest. You'll have to show that tau. This is the question. Smallest, it is coming that point. Because quotient topology, otherwise you won't appreciate a lot, because it is the other direction. But you answer this question. Product topology handle basic open sets and the projections. That is good enough. Okay, so right. I won't take class on Friday. Tomorrow I'll take class, so I want to teach a little more. So think about it. I am coming back. Now I want to talk about just idea. I want to give the quotient topology. Okay, you can look at that. Think about it. And then I will just give you the idea of the quotient topology. I won't finish quotient topology. Of course, quotient topology I need to talk a lot. Let's see. Hello, let me start. I think you have understood my question. I am saying I wrote very clearly that is the smallest topology such that this each pi is continuous. That you do it. Why I'm talking about, because quotient topology is exactly the opposite direction. Okay. Now suppose I'm doing the only one thing, that suppose you have a space here. And you do not have a topology, but you have a map. You have a map. Hello, you have a map. Now the question in the opposite direction. Now look, if I give here trivial topology, trivial topology. Okay. Suppose sigma is a trivial topology. That means only y and phi. Then obviously f inverse y, x, f inverse phi is phi. Obviously x and phi belongs here. So this will be continuous. So the trivial topology is the smallest topology on y. You can think of that. So the answer is trivial. So here the question will be what? The strongest topology. Does there exist the strongest topology? Sigma. This sigma is different on y such that f x tau well again look that first of all whatever topology you think, how do you think of that? Already I gave you the idea there. Now it will have to work in the different way, but a different direction. So that here you need to define. The gap is here. Gap is here. But if you want to make it first of all continuous, look, whatever topology you take, okay, that means I need this f inverse p look. All I need to know this has to be here. That means f inverse b belongs to tau p subset of y. This thing take. Look, first of all, here it's a p subset of y. Take this sigma. Look, I am going through f inverse. Okay. First of all, look, does it give a topology? First of all, strongest topology other than trivial topology, what will be this? That I will handle. Now the question is this: does it give a topology? That of course in the f inverse b. Okay, look, you take b equal to y, that is x belongs to tau. B equal to phi, that is here. That is, and if you take 2 b1 intersection b2. Don't confuse with any subset. So f inverse, that I already told you, there is no problem. But you have taken from here. So this belongs to tau. This belongs to tau. Tau is a topology. So this belongs to tau. So by this definition, this belongs to sigma. Okay. Similarly, if you take f inverse union pi arbitrary, says sorry, any I. Any I. Each of them is in tau, but tau is a topology, so that this whole union is in tau. So this is in tau. So that means this is in sigma. So sigma is a topology. Okay. So that what I am doing it here.
Sir, what if we take the collection FB such that B belongs to tau?
I'm working this thing. Let me finish that. My collection is this exactly. My collection is this. B subset of Y such that this is the condition, F inverse belongs to tau. And I have proved sigma is a topology on that. Exactly, I proved. I checked. Sigma is a topology here. Now I said the strongest topology. That means, what does it mean? That means if you take, suppose this, some Y alpha from topology, such that this F is continuous. So I need to check alpha contained in tau. Okay, here I should assume that there is no problem. But now you assume onto. So you will see required F12. Until now I didn't require onto. But now you will require onto if you want to prove that. Why? Now F is continuous, suppose. Okay. So take B subset of Y, B belongs to alpha. See, if this is continuous, implies F inverse B belongs to tau. Do I need onto? I will come that. I thought. But F inverse B belongs to tau. But that exactly by this condition, it means B belongs to sigma. That means that is so. This one is mean now you don't need it. So this is the thing. Any topology which makes F continuous is weaker than this. Because here I have taken the all possible things. Okay, that F inverse belongs to tau. Okay. So this is the thing. So this is the strongest topology. This is the strongest topology. Okay. So this way you get this. Now the quotient topology that will come. Okay. What will be the quotient topology? Well, this actually is called the quotient topology. Say why it is called quotient topology. Usually quotient topology they take F onto. Quotient topology on Y generated by the map, that map generated by F. Okay. Well, look, in order to define the quotient topology, I do not need it to be onto. Okay, this is onto. But I want to, let me tell you that in Aliprant's Parkinson, the problem, Aliprant's Parkinson, page 65, that's the thing. Problem 20. Problem number. Look. He has not given onto, but later on I will need it. Okay. Right. So the 20A. He's calling this quotient topology tau F because you need both tau and F, not only the F. The quotient topology. Okay. The quotient topology determined by this. Okay. Look in part C. Okay. So that let me explain again. Suppose you have a map from X tau to Y. This sigma is still not there. Okay. Suppose you have a map. So obviously you can't talk about continuity anything. Now I want the strongest topology on Y, strongest topology such that F is continuous. Because smallest topology, I know the trivial topology. To take sigma equal to this, so this collection, all this collection, such that F inverse V belongs to tau. Okay. So look, this collection is non-empty. At least Y and phi are there. Okay. So this is non-empty. And I'm saying sigma is the topology on Y. That I checked. Okay. Right. And this is the strongest topology for which F is continuous. That this is the proof. B subset of Y, B belongs to alpha. Since I am assuming F is continuous, F inverse B belongs to tau. But by this definition, B belongs to sigma, so that alpha is contained in sigma. So that this is the strongest topology for which F is continuous. This is called tau F because this depends on F as well as on tau. Okay. Now the thing is that how do you know that suppose actually the question in the other direction that Aliprant's 20C he handled. Suppose you have a topology, you have some continuous map. How do you know this is a quotient topology? Because you may ask me that why I need to bother whether it's a quotient topology or not. That you need to bother because quotient topology gives many useful spaces. Okay, right. So that if you have quotient topology, now the thing is that for that he's saying take F x tau y sigma. Suppose F is onto continuous, that is the reason I introduced open. Continuous open. Okay. Onto this thing you need. You will see that why you need. But this is not some restriction. Usually in the exam, good nice examples you get that. Onto continuous open. Suppose you have it. Then sigma equal to tau f. That means sigma is the quotient topology on Y given by tau and f. Okay. Now how to define quotient topology? That means you'll have to show again this that tau f. Remember the tau f is this. Okay, F inverse V belongs to tau. Look, already we have proved that this is the strongest topology for which this is continuous, and with respect to sigma, it is given continuous. So that this is this. This is immediately proved, provided you know the previous thing that I proved. This is the strongest topology for which this map is continuous, and here it is given it is continuous. So that this is. So all I need to prove that I need to prove this. Okay. I need to prove this. Got it? Well, take this. Look, now we'll see why. Take V belongs to tau f. V belongs to tau f implies F inverse B belongs to tau. Now, F, it is given open, implies F inverse B belongs to sigma, since F is an open map. But now look, why you will need onto? This will be onto provided it will be equal to E B provided F is onto. Because when you are taking pre-image and we are going back, you may not be able to recover the whole thing. Look here, X, Y. Suppose this is not onto. So suppose this much you are covered by the map. But if you take this B, then when you are having F inverse V, and then if you take F, you will be able to cover only this much. Only this much. You won't be able to cover this. But if it is onto, then you will be able to cover the whole thing. So yes, F is onto. So B belongs to sigma. B belongs to tau f implies B belongs to sigma. So that is true. I have used everything onto continuous open. Okay, so this will be a quotient topology. That's exactly Alipranthis 20C did. But this is very important. Well, what about if it is closed, it will be true also? If instead of open, if I take closed map, will it be true? Hmm? Well, let me see that. Look, V belongs to tau f implies y minus b is closed in closed in y tau f. ठीक है? Implies f inverse y minus b, which is f inverse y minus this is x, f inverse b. The f is continuous, is closed because this is continuous with respect to this also, is closed in x tau. Now if you have closed map, implies f inverse y minus b equal to this is closed. Okay. I think this I don't need this. Is now look, if you have closed map is closed in here, this is closed map. So I see. But this is same as f is on to is closed in y sigma, so that B is open in y sigma. So that instead of open, you can take closed also. So that what I have got, let me write down this result. First, let me write this thing. What I have done, look what I have done. Let f x down y be a map and sigma equal to this. What I'm getting. Result, let me write. Then sigma is the strongest topology. That automatically will say. So you can first write is a topology on y. Okay. Moreover, sigma is the. Some of you are interested in algebraic topology or differential topology. You should pay attention to this. Okay. Then is the strongest topology on y such that f is continuous. That is, I can write that. That is, if fx tau y alpha, alpha is a topology on y, is continuous, then alpha contained in sigma. Okay, right, first you got. Now, okay, sigma. Usually, now, sigma is denoted by tau f and is called the quotient topology. Quotient topology on y. Quotient topology you need both tau and f generated by tau and f. Okay, and this, take this, is called a quotient space. I am saying because if you change f, you will get probably another quotient space. It's called a quotient space. But with respect to tau and f, if they are fixed, then it's called the quotient space. It's called a quotient space of x. Okay, right? That you have got. Now, second thing you got result, that is 20C of arithmetic. Let f x tau y sigma be a surjective continuous map. Pn, that means onto continuous map. Onto continuous. Now what I am writing, if f is either open or closed, both, any possibility. I'm not saying both, any one possibility. Both, sorry, either open or closed, any possibility. Only one. Then sigma equal to tau f. That is sigma is the quotient topology. Tau f on y. Got it? Well, I think Horst gave this. Now look, quotient space to मैंने दे दिया. I will just talk to give some examples. What is the nice examples? Now look, in R, suppose I'm taking this map. What this map I'm taking? 0, 1, 2, R square. Look how next time I will talk about identification spaces or partition spaces. Now look, if I give this map, X. What will give this? I think I wrote it correct. Cos 2 pi x, sin 2 pi x. X lying in between 0 and 1. So that angle is between 0 and 2 pi. Here, the angle. So what you are getting? You can easily check this is continuous because each thing is continuous. So continuous. Okay. So that instead of r square, if you take this thing, S1. S1 the unit circle. Unit circle means centered at the origin with radius 1. This is a standard thing in function analysis also. The unit circle in R square. Look, this is onto. This is continuous because this 2 pi x is a composition of two continuous function. F is continuous onto. Is it open? Well, I do not need that. You can take that. If it's open or closed on that. Open or closed. Okay. Look, what I'm saying, S1 is a quotient space. It's the usual topology. Is a quotient space of, call it I also here, 0, 1. You should check whether it is open or closed on that. But it's a quotient space. If you can check one of them is true, then it will be a quotient space because it is continuous onto. Okay. Now the thing is that is the analytical description. Okay. But if you go for geometric view, what actually you're doing? Look here, you have this 0, this one. When you go to the circle, you're starting here. You're going this direction. Okay. Look what I am doing. Here it is 1 to 1, except only a pair of points, 0 and 1. Otherwise, it is 1 to 1. Okay. Right. You can visually you can see that whether it will be open set or not. Okay. Right. Or closed set or not. Okay. 0, 1. If it is open set, it will be like this 0 to 1 like that. You should think about it. That I will come later on. Now what I am doing, I have this, you can see that string, everything I'm leaving as it is except two endpoints. I'm attaching them. I'm attaching them. Two endpoints. That means two endpoints, I'm identifying them as the same 0 and 1. Nothing else I'm doing. That is the difference between this and this. Essentially they are same except at this point the 0 and 1 are being identified here. Okay, so that quotient space also we get by identifying some points, identifying by points. Okay, so here is an example that I am getting S1 unit circle as a quotient space of this, but you should convince yourself that why is quotient space on that, because it is continuous, it is onto. If it is either open or closed, then it will be quotient, or else you can prove it directly that here you are getting it is a quotient topology or not. Okay, map is given. Okay, right? Map is given. So you can take that. So this is the idea that identifying quotient space basically come interesting examples. But that I told you that whether you do geometric topology, differential topology, even algebraic topology, that's the thing. Identifying some states like here I did, but suppose I'm just telling you the last thing. Suppose you have this thing. Rectangles. Suppose I identify these things. Suppose I identify AD and BC, two sides. That means I'll have to flap like the fold. Then what will you get? You'll get a cylinder. Okay. Right? So that's the way it comes. So I will discuss tomorrow on that again. So right now you should study product topology, and you will see that what is the interest with the product topology, a connection with the quotient topology. Look, one connection you already got. You got this. If you have a space x1, xn, of course tau I, In the product topology, you got this pi I. This is onto that I proved. Continuous, open. So these are the factor space. So that means each factor space, this is the one of the finest examples of quotient. Each factor space is called the factor space. Is a quotient space of the product space. Well, if you have done some topology on that, is it quotient? Something quotient should come. Well, now look, if I do it, that I am leaving it, I am not going to continue in the next lecture on that. That you should think that why it is called a quotient space on that. First of all, you look why homeomorphism was there. X1 cross to Xn. This is a product topology, of course, Xn. But I can interchange their positions. Suppose I take this. Interchange the position of X1, X2. That will give you another product space. Will it be different from this? It won't be actually different. They will be homeomorphic. That's another advantage of product topology. If you change the place, it doesn't matter. Homeomorphic. Okay. Now look, I could for xi, whether this will be true or that, I will have to define something that I do not know how to do that. That if you have X topological space, and how do you define this? Even if you think Y is a subset of X, how do you define this? Okay, so that is another thing. If you can have something that look, if I by factor other than xi, that means xi plus 1 up to xn, then it should be homeomorphic to xi. Actually, it comes like that for the nice things in that. If you look for each xn, you take r, then you can see that is coming this thing. So that is the actual justification why it is called a quotient space. Okay, because r to the power n, and if you take that one, except another copy, that Ri, that will be isomorphic to Ri, topologically homeomorphic to Ri. So that is the reason why it is called quotient space. Actually, it is not arbitrarily, it has been called quotient space. Okay, so I will dwell on the quotient space. Actually, I will give some examples. Quotient space can be viewed in two other ways. Okay, right, that I will discuss. That is, Willard has given very good descriptions. I've given good descriptions of some quotient spaces on that. So that I will teach you tomorrow. Tomorrow I'll have the class, but Friday I won't have the class. That means other than tomorrow, I won't have any more class this week. Okay, see you. Bye tomorrow. See you tomorrow.
Evening, sir.
Bye. Do
Sir.
you have any question?
Yes, sir.
Hello? Batao?
Yes, sir. Sir, in the last lecture, you have told that any homeomorphic function,
Huh?
that is any homomorphic bijection function from an interval to interval, if the length is same, then it is isometry.
That I'm saying, I don't know why you are confused. I said bijection function, not homeomorphic. I said, look, I said two intervals, two open intervals to take. Open intervals, take the bounded interval, are always homeomorphic. That you can prove. Basically, you need translation and the change of scale. Basically, you need to move A to C, B to D, and then you need change of scale. That you can always do. But what I said that A, B, and C, D will be isometric to each other, or isometric, the usual with the usual distance, isometric to each other if and only if you have this length is same. This is the thing I was telling that I told you. This is the thing.
If we consider a
I
function,
think you should check your example very carefully. Yeah, I do consider. You should check your example carefully. You are writing even no close interval. You are writing it is open interval. But check your example carefully, and you can write to me. If you then this is the isometric to if this is not a problem, okay. And if you are saying isometric to each other, then by diameter you can do it, or you can prove directly also. Okay, if you don't do that. If you are isometric to each other, then obviously it will help. And if you have this, you can prove the isometry. You need only some translation. For this, you just need some translation. If you have this. On the other hand, if it is isometric to each other, okay, suppose this is an isometry. Okay. Here you are assuming this is an on isometry means onto isometry. Onto isometry, not one-to-one isometry, onto isometry. Usually we don't mention the knowledge. I am saying isometric to each other. That means obviously it means onto. Okay. If I want to isometry, then you should say that look, first of all, what will be FA and what will be FB? Just think about it. What is your choice? Okay. I said onto isometry, then you must have it. If you don't have it, then what will happen? I said if you have this, it implies you must have that. If you don't have it, then what will happen? Okay. That you are yourself is saying is the diameter, it must have it. Then what is the problem? That you are saying. Only thing you'll have to check the what your argument diameter, that is correct. Then you are saying if you have this, then we must have this. And for this, so other way it is easier. You just take the translation. Since the length is same, A, B, it doesn't matter. Even you can take CD. I am just taking CD. Length is same. So you take this. That means what will be happen? A will have to go to C. That means what will be the translation? Huh? That means A plus X has to be C. Okay. That means X is C minus E. That means each problem will have to take Fx equal to, okay, why? Don't confuse with this. Take T. Fx equal to okay. I think C minus A, or what will happen? Actually, you'll have to this. Okay. C minus D minus C equal to B minus A. We are assuming. Okay. So that F here FA equal to C. Right? And FB equal to B plus C minus A. But you are saying D minus C equal to B minus A.
We can take a line from A comma B to C comma D. Vision line.
Yeah, this one. What is the problem? If
Sir, actually I thought
I get a simple question. Yeah, I think you thought something wrong. That's something.
Yes sir, I thought कि वो हर होमोमॉर्फिज्म इन दो इंटरवल के बीच में हर होमोमॉर्फिज्म आइसोमेट्री होगा. मैंने वो सोच लिया actually.
FB, wait a minute. You're getting B plus C minus E. And what you are getting? D minus C equal to B minus C. This is equal to T. I just asked this question and this question. Nothing else. Okay, right? Got it?
Okay,
Any
sir.
other question? Make
Yes,
sure
sir.
that you complete the note and send me. Okay? And
Yes,
also
sir. Yes.
correct that interval. समझ गया? Because you
Yes,
are
sir. Yes.
trying to have one-to-one bijection. That's why you did. But in the beginning, you
Yes.
didn't correct it. Okay?
Yes. Yes.
After you send me the corrected one, I will post it. Okay? I checked it very carefully. ठीक है? Okay, bye.
Thank you.